As this header indicates, low-vision clinical exams require a specific approach. Standard visual acuity is typically measured at 6 meters, but many low-vision patients cannot see the largest letters from that distance. The most direct solution is to reduce the viewing distance. By physically moving the patient closer to the chart, perhaps to 2.4 meters or 1.2 meters, we increase the angular size of the letters on their retina so they can be identified. This physical shift predictably alters the math. We use the proportionality rule to convert these non-standard test distances back into a standardized clinical Snellen fraction, keeping the viewing angle constant. Testing at closer distances acts as a controlled variable. It allows us to mathematically reverse engineer the patient's true acuity limit. The formula is a ratio. Test distance over letter size equals 6 meters over the equivalent acuity. Let's apply it. 2.4 meters over size 60 equals 6 over x. Cross-multiplying gives 2.4x equals 360, so x is 150. The standardized acuity is 6/150. Standardizing the denominator ensures clinicians can accurately compare a patient's vision across different testing environments. Distance acuity alone omits critical data. To prescribe effective reading aids, we need to accurately predict a patient's near vision based on their distance results. We use the near bridge formula to translate the distance denominator into an n notation point size. The distance denominator equals expected near size multiplied by 3. For a 696 equivalent, we divide 96 by 3, yielding an expected near acuity of n32. This conversion specifically assumes a standard reading distance of 25 centimeters. If the patient's actual near vision falls short of this prediction, it immediately signals clinical complications like visual field scotomas or poor contrast sensitivity. Mathematical calculations rarely yield perfectly clean numbers. The exact values we calculate often fall in between the standard print sizes available on clinical near vision charts. A calculated denominator of 96 does not exist on a standard chart. The clinician rounds to the nearest standard line, which is 6/95. Rounding ensures the resulting prescription can actually be constructed. Trial lenses and standard magnification aids are manufactured in specific dioptric steps, not infinite gradients. The calculation sets the target. Adapting that target to standard optical intervals makes the prescription viable in the real world. Let's solve a practical problem. A patient can currently read N16 print at 40 centimeters, but their goal is to read N6 newspaper print. We need to find how close the material must be held to make N6 print look as large as N16 print. We invert the proportionality rule, setting up our ratio to solve for the target distance. The target size of 6 multiplied by the current distance of 40 divided by the current size of 16 gives us exactly 15 centimeters. We round this up to a clinically standard working distance of 16 centimeters. Establishing this new equivalent viewing distance is the essential first step before selecting a stand magnifier or determining the lens add. Once the target distance is locked, we calculate the near addition required to focus the eye exactly at that working distance. We divide 1 by the required distance in meters. 1 divided by 0.16 meters yields plus 6.25 diopters. For standard trial frames, we select the closest round interval, a plus 6.00 diopter lens. These steps form a complete workflow. First, standardize distance acuity using the proportionality ratio. Second, estimate near vision with the n notation bridge. Third, calculate the dioptric power based on the new equivalent viewing distance. Mastering these calculations removes the guesswork. It allows clinicians to reliably select an exact optical tools a patient needs to read, navigate, and regain functional independence.